Hi, AP Chem. This video lecture is for 3.10 to 3.12. So we're going to be talking about solubility and then spectroscopy and the electromagnetic spectrum and properties of photons. I recommend while you're watching this, I've already pre-written out all of the notes. So on your iPads, you should pull up that copy of the notes so that you can kind of pause as you go and copy as necessary. It seemed like a waste of time to have you guys just watch me write stuff. So go ahead and have that out and then we'll continue. 3.10 is solubility. So we just finished talking about 3.9 and 3.8 where we're talking about solutions and mixtures and homogeneous mixtures and how we are separating them. Solubility is a topic that's familiar to us. It's will it dissolve? Will it have those attractions that will allow us to? So for a solute to be soluble in a solvent, the solute-solvent attractions have to be greater than the solute-solute and solvent-solvent attractions. When they mix together, they're called miscible. We see this word a lot, miscible. Dissolving covalent molecules, the big idea we learned in our lab yesterday is called like dissolves like. So for example, we know immiscible liquids like oil and water aren't going to mix, but molecules that have similar polarities or ions in polar liquids are going to be miscible because they have charges. And so the more like a solute and a solvent are, the more likely they are to be soluble in one another. So that's that little bit on that page. Moving on to page 25. So here's our general rules. You've seen the solubility rules before. This one is kind of our cheat sheet. Mostly to memorize is just these few. You don't need to memorize all of them. But knowing that all of my alkali metals, my lithium, sodium, potassium, rubidium, etc., are always soluble. Ammonium and nitrate are always soluble. Those are going to come up frequently, so you'll want to memorize those particular rules. Soluble ionics are conductive, which means they're electrolytes. So when we have a conductivity tester or a bulb of some sort, they will light it up because of those free-moving electrons, right? The ionics, as they separate. We know that ionic compounds, when they dissolve in water, are free-moving electrons allow us to conduct electricity. If the ions form an insoluble compound, it's called a precipitate. Not sure what happened there, sorry about that. If ions form an insoluble compound, it will form a precipitate, and that's just the picture. Precipitate is our fancy word for if my two solutions combine to make some sort of ionic solid, then the solid we consider a precipitate. It's kind of a solid in fluid. And that's it for 3.10. So on to 3.11, which is our biggest topic. 3.11, spectroscopy and the electromagnetic spectrum. So spectroscopy and the electromagnetic spectrum. The electromagnetic spectrum is familiar to us from physics. We like to abbreviate electromagnetic spectrum as EMS. So that's just good to kind of know as we go forward. And we're looking mostly at frequency and wavelength. So we've got a Greek symbol nu, which is kind of like a V with a curvy side, is our frequency symbol, Greek symbol nu, and then lambda is for wavelength. And the difference in our electromagnetic spectrum is the frequency and the wavelength, how much energy the different waves have. And so you can see our spectrum, we have radio waves are the lowest energy, lowest frequency, highest wavelength down here, and then high energy over here. You can, the waves are pretty explanatory. We can see our frequency, we're getting way more frequent as we go to our more energizing waves over here, examples of each of those. It's important to kind of memorize the order. It's good to memorize the whole order where we've got radio to microwaves, infrared, visible, ultraviolet, X-ray, then gamma, but particularly those around the visible. We see a lot of the micro to UV we're going to see in this particular section because those are the wavelengths we tend to use to classify substances. And so knowing who has the most energy of those, my ultraviolet is the highest energy, my microwaves are the lowest energy, and those different wavelengths teach us different things. Microwaves are going to teach us things about rotation, infrared about movement and speed, and then my visible and ultraviolet as we get more and more energetic. All right, so starting with spectroscopy up here, we've got two different types. It's the study of matter's interaction with the electromagnetic spectrum. That's kind of what spectroscopy is overall. There's lots of different types. It's pretty much always used to identify a substance when we don't know what it is. First type is infrared spectroscopy, IR spectroscopy. And I gave you just a little example of the graph there. We have wave number in centimeters -1, so 1 over centimeters, and transmission on my y-axis. It's used to identify molecules based on how they vibrate when exposed to infrared radiation. So infrared radiation is going to tell us about vibration. Infrared radiation is going to tell us about vibration. And infrared radiation we feel as heat, so I like to remember that because vibration is movement, and we only can feel infrared, we can't see it, so that's how I like to remember that one. Photospectroscopy is measuring which wavelength of light gets absorbed by a sample. So we have wavelength on our x-axis and then absorbance on the y-axis, and that's measuring who's getting absorbed. So photospectroscopy, we're kind of taking a snapshot of light passing through that sample. When radiation interacts with particles, they can cause vibrational motion, right? Infrared, I like to remember we can feel it, it's movement. And microwaves are going to tell us rotational motion. And so if you're given a spectrum and we notice that the particle or the substance is interacting with infrared or microwaves, then we can make conclusions about that vibrational or rotational motion. We'll see some of that in the practice problems. Electron transition, so that's when my electrons are absorbing photons and jumping up to higher energy levels. So this is complicated. Definitely pause here so everybody can finish copying page 26 before I go on. Electron transitions are when energy is absorbed in the ultraviolet visible range, causing electrons to jump to higher energy levels. So my photon with a certain amount of energy will hit an electron in the ground state, causing it to jump up a certain amount of energy, and that energy matches. So whatever energy the photon had, whatever range it was in, whatever color it was, if it was visible, causes that same amount of energy to jump. So we can tell how much energy got absorbed based on the light that passes through. That's spectrophotometry. The energy needed for the electron excitation is called quantized, and then some specific information on that. A photon with a specific amount of energy is needed to make it happen, so not every type of photon will be able to make, not any type of light or type of energy is going to make this be able to happen for different transitions. And it's a set amount of energy needed because there's a set number of orbital subshells available per substance that's being tested, per element that's being tested. It is possible to jump a half shell. This makes a lot more sense when we see some of the ways that the data is represented for this. So let's look at an example, and then let's look at a spectrum to kind of see what we might determine. The takeaway from this, though, is my photon energy being absorbed by an electron jumping up is mappable. So that X amount of energy from the photon is the same as that electron jumping X amount of energy. So the energy is the same. So we can use that as valuable data. All right, next up, we've got examples. So let's look at our first example. It says, nitrogen molecules absorb ultraviolet light, but not visible light. Iodine molecules absorb both visible and ultraviolet light. Create an explanation for this. So the first thing I notice in terms of my different lights is that they have different energies. Ultraviolet is more energetic, visible is less energetic. So what we're seeing is the iodine molecules are absorbing both lower and higher energy light. So that's what our explanation is going to talk about here. So it says both ultraviolet and visible we're looking at electron transitions, right? That's a callback to here where it's not infrared with vibrational motion, it's not microwaves with rotational motion. Both ultraviolet and visible, we're looking at electron transition, so that jumping up or down. Ultraviolet has more energy, right? That's what we talked about, than visible light. So iodine must have some lower energy transitions available in its electron configuration. We know that because iodine absorbs visible as well as ultraviolet, whereas the nitrogen doesn't absorb visible light. So my iodine must have some lower energy transitions available because visible light is lower energy than ultraviolet. The next one is going to be, we have an example of when we have the infrared and the microwave as well. So this is our example here. The absorbance spectrum of a pure substance is shown below. What effects would we expect the absorbed radiation to have on the molecule? So we see a range. We see in the ultraviolet, in the infrared, and in the microwave. And each of those tells us different things. My ultraviolet and visible, as we saw in this previous question, both of those tell us, excuse me, both of those tell us electron transitions. My infrared, as we learned on the previous page, is vibrational motion. And then my microwave is telling me rotational motion. So pause here, finish copying, and then let's dive into 312. All right, 312, properties of photons. So for properties of photons, we have wave-particle duality. You may have heard that if you took AP Physics or not. But what that means is that super teeny tiny particles like photons act like both particles and like waves. They act like particles in that they have mass, Even if it's a teeny tiny mass, think like electrons, not protons and neutrons. And for the moment that you look at it, it also has a specific location. But mostly, they act like a wave. They have wave-like properties, which means we can use wavelength and frequency to determine their energy. So here's my two equations, and both of these have constants in them that are available on the formula sheet, which is great. So my first is if we're calculating energy of a wave, we can use Planck's constant and frequency, and Planck's constant as well as the speed of light are both on our formula sheet. So we don't have to memorize them, but we do need to know what they stand for. And then here we have for energy, if we're calculating, if we're missing wavelength or frequency, then we can use our speed of light, which is a known quantity, 2.998 times 10 to the 8th meters per second, to determine either our missing wavelength or our frequency. And then you can see here we've got a picture of my ground state versus my excited state. So my photon is hitting my electron, causing it to jump to my excited state, and that energy of the photon that hits it is the same as the energy of whatever that transition required. So we can use that as a direct measurement. And that's going to help us because we can use Planck's constant, and if we know the energy or we know the frequency, we can calculate the missing value. So my photoelectric effect, if a photon with enough energy hits a substance, it can remove an electron from that. And remember, removing an electron is ionization energy, which we learned about, I think, back in Unit 1. So if a photon with enough energy hits a substance, then it can remove an electron from it. It is not about the intensity of the light, it's the energy of the light. It needs enough energy to overcome that ionization energy in order to free that electron, free that electron. You can calculate or assess using ionization energy or binding energy, or you can compare to frequency or wavelength using equations. Let's see an example. So let me go through this example before you copy it down, and then you can copy it down. The complete photoelectron spectrum of an element in its ground state is represented. Calculate the wavelength in meters of the electromagnetic radiation needed to remove an electron from the valence shell of the atom in this photoelectron spectroscopy. So we've got my PES, which we learned about in Unit 1. So we've got my binding or ionization energy at the bottom, my relative number of electrons. You might need to review what these mean, but if you remember, it's just direct electron configuration. So we've got like my 1s2, my 2s2, my 2p6, my 3s2, etc. But that doesn't matter because it specifically says it wants us to calculate wavelength. So we're going to rearrange our equations to find wavelength with our known information. And it wants specifically the energy, the wavelength of electromagnetic radiation needed to remove an electron from the valence shell. So what we need from here is the valence, which is our last one, right? Our easiest to remove here. So we have that energy. Now we're going to rearrange and plug in. So I have my energy is equal to Planck's constant frequency, and my speed of light is equal to lambda times frequency. So what I'm going to do here is I'm going to plug in into my energy equation instead of frequency. We're going to plug in my C lambda because we need lambda. That's what we're trying to find. And then I'm just going to rearrange my equation to solve for lambda, which you don't have to do. You can plug them in here, but I just like to rearrange my equation. So now we've rearranged it so we have wavelength, which is what we want, right? Wavelength in meters is equal to the speed of light times Planck's constant. Both of those are known values, which is great, over the energy of my valence shell electron. So we're going to plug that in. We've got my speed of light times Planck's constant divided by the energy of that valence shell. And it's a good check, right? If we check our units, they should cancel to get what we want. We need meters. It wants wavelength in meters. So I've got speed of light is meters per second. We've got Planck's constant, which is joule seconds. So seconds over seconds cancels. And then my joule seconds, I've got joules in the numerator here, and then in the denominator for my energy, I'm left with meters. So I just plug everything in. I get 2.02 times 10 to the negative 7th meters. And then I just added a note here in case it asks for nanometers, which would be very common. This is the conversion factor. And as of next year, we actually have the nanometer conversion is now finally on our equation sheet as well. This is new. This used to be on the other science AP exam equation sheets, but it wasn't on ours until now, so that's pretty awesome. So that's just there as a note in case we needed to convert into nanometers, either before or after we did the conversion, depending on what units we were given in the problem. All right, I think that is it. That is it. Awesome. So rewatch as needed. You guys have the notes, and then the rest of class, you've got your extra notes worksheets to work on, and practice problems, of course. See you tomorrow.